the seminar of our series, of our program here. So I, Shaun Lovejoy from McGill University, is an expert in various things, including turbulence and multifactor properties of flows and of precipitation. So today is going to talk us about this aspect on weather emergent and multifractal cascades, and I think this is the first. There will be a follow-up later during the program. So please.
Good morning. I guess that works. Right. This is a bit of a unabashed, unashamed plug for my book with Daniel Schertzer. Just came out a few months ago, and so as Valerio just mentioned, I'm going to, in 2 weeks, I'll have a sort of a second part, which is going to be focusing on the longer time scales, essentially climate scales, or what I call macro weather and climate. I'll explain what that is at least shortly, but I will focus on weather scales, space and time today. All right, so what do we mean when we talk about emergence? So I put in the title Emergent Laws. Well, emergence is a kind of a notion that's often invoked in the complexity theory, but in fact it's a pretty basic aspect of scientific theories in general, and specifically physics. Science is a kind of a hierarchy of different models and theories. There are fundamental theories such as quantum mechanics, which, as far as we can tell, is absolutely valid, but of course for macroscopic systems, most of the time it's pretty useless because we have so many particles, and so we're often, especially in geosciences, quite happy to use classical mechanics, but even classical mechanics, of course, is not useful unless we go to sort of a continuum mechanics kind of limit, thermodynamic limit. And so we're used to using then higher level theories. And one little comment here is that often we go from a stochastic theory, say, to deterministic, and then we'll see that in the case that I'll be discussing, we're going to go from a deterministic theory, essentially continuum mechanics and thermodynamics, to a kind of statistical theory of turbulence at high Reynolds numbers. So this is all kind of very classical idea that if you go to very strongly stirred fluid system, high enough Reynolds number, that you get some kind of new laws that emerge, right? This is sort of the pioneers of turbulence, Richardson, Kolmogorov, Bolgiano, etc. This was their idea, that there would be laws, and of course they each have their own law. There's the Richardson 4/3 law, dates from the 1920s. There's Kolmogorov law, which is actually, in fact, at some level, a minor variation on the Richardson law. You've got Corson, Obukhov laws for passive scalar advection, and you've got Obukhov and Bolgiano laws for buoyancy-driven turbulence. And so if you're at high enough Reynolds number in hydrodynamic turbulence, then you get this kind of what's sometimes called the spaghetti plate view of fluids, where you've got here the dark shading is vorticity. So the idea is you have the vortex tubes are kind of bits of spaghetti that are all tangled up, and so this is actually from a numerical simulation. But in any case, all of the classical laws of turbulence are written in this kind of a way. There's some fluctuation for the Kolmogorov law here. I'm giving the example, say the fluctuation in a velocity component, delta V, for 2 points separated by vector distance delta R, would go then as a turbulent flux. In fact, it's the energy flux to a 1/3 power, then times the separation distance to, in fact, the 1/3 power. But this is the kind of generic form of all these laws. And of course, it was, Kolmogorov, for instance, thought that this law would only hold up to something like 100 meters in the atmosphere. because, first of all, it's an isotropic law, right? It's just the modulus of the vector separation. It doesn't matter what orientation. If you go up or down, the law is the same as if you go left to right. And clearly, there's a problem of stratification in the atmosphere. Also, the way Kolmogorov argued for his law was that you needed more or less a constant energy flux. In fact, he put it in terms of energy dissipation at the small scale, but you could extend that to mildly varying energy flux, energy dissipation, such as, say, quasi-Gaussian. But of course, in the real atmosphere, almost all of the fluxes are concentrated in very small regions, storms, centers of storms, etc. And so clearly, this is a very poor approximation, problem of intermittency. So just before I go on, just a last kind of introductory comment, which is that I mentioned there's a relationship between emergent laws and complexity. Basically, the thing is the emergent laws are higher level laws, they're simpler, and it therefore corresponds to a kind of reduction in the complexity of the system. And in fact, if you use all the emergent laws that you can, then what's left is a kind of an irreducible level of complexity. So really, you ought to be using, for example, continuum mechanics instead of statistical mechanics if it's justified, of course. For example. And so I'll be arguing the same kind of thing, that really we ought to be doing fluid mechanics using these higher level laws, at least when we have high enough nonlinearity. So, okay, so all the laws are of this basic type. Fluctuations are some turbulent flux times a scale, some power h. But, so the question is, sort of typical thing that arises in physics, you come up with some law and it doesn't work very well. That would be the case of the isotropic turbulence laws when you apply them to the atmosphere. So either you throw them away and come up with something different and better, or you generalize them so that they're applicable. So what I want to do today is describe how, first of all, you can generalize the turbulent fluxes so that they're highly intermittent and multifractal. In fact, the notion of scale has to be radically changed as well to take into account anisotropy, especially stratification. And even the fluctuations, well, we can, for the purposes of today's talk, we can more or less consider them just as differences, but actually we need something a little bit more sophisticated in general. And of course, wavelets gives a general kind of theory about fluctuations, how to define them in different ways. So I'll come back to that in 2 weeks from now, because they'll be absolutely necessary for the climate, in fact. And of course, this law is the same kind of thing in the Fourier domain. So I'm going to just show some quick examples. But so you have basically the variance, say, of the observables per wave number is equal to variance of the flux per wave number times the wave number to some exponent. Okay, so space you get power spectrum like this with some exponent, time like that, and this will be assuming, of course, isotropy still in the horizontal. Say if k is a horizontal wave number. So this still, I'll discuss anisotropy a little later. Okay, so I'm just going to quickly show you that actually this type of scaling holds up to planetary scales very nicely. This is just some satellite imagery, tropical. This is the tropical rainfall measuring mission, which is a satellite with an active radar, in fact, but also with many different wave bands, including visible here, a couple of thermal IR bands, and then some intermediate bands. And you can see that the scaling is actually quite excellent over the range right up to 20,000 kilometers. And, well, the fall off here is basically due to the resolution of the instrument.
Sorry.
Yes?
So here you're averaging over various bands.
Yeah, it's 1,000 orbits, which is this period here. It's about 3 months. Yeah, so it's essentially every 90 minutes you get an orbit, right, roughly.
Bigger is a bit less than 5.
Yeah, it's a little less. Okay, I could go into all that. Of course, it turns out that if you had a passive scalar and no intermittency, you would get 5/3. With intermittency, it will be a bit less. So actually these slopes are something like 1.5, 1.55. It changes a bit with the wavelength. So and if you, anyway, you could do some radiative transfer that I won't have time to discuss, but so it actually should in fact be not too far from passive scalar value. This is the same satellite, same orbits, but in passive microwave. The resolution is a lot worse, but you can see that you get excellent scaling once again. You can look at, this is aircraft data. Okay, there's all kinds of problems with aircraft data. In fact, when you look at the velocity, the wind, as I will discuss a little later, but these are for the other fields, potential temperature, humidity, temperature, actually 280 meter resolution to over 1,000 kilometers, very nice scaling. Similarly, you can look at reanalyses. A reanalysis is some kind of hybrid product between data and a model, right? It's just sort of, you constrain your, you're trying to estimate atmospheric fields using essentially the equations to constrain the measurements in some optimal way. So you can see that, in this case, up to about 10,000 kilometers, most of the fields are really quite nicely scaling. Also, just the last one in this series, also, of course, you want to try and understand how that's possible. You have to worry about the boundary conditions. One of the boundary conditions, of course, is the topography, and the topography is also rather nicely scaling. So, okay, so, and after this, I'm just doing a kind of a quick tour of the empirical side of things. Of course, one could also consider things in time. Now, if the wind field is scaling up to essentially planetary scales in space, then one would expect everything to be scaling in time up to essentially the lifetime of a planetary structure, which turns out to be about 10 days. And once again, I'll come back to that. So what I've got here is data from two data sets, essentially. I've got reanalysis. Actually, this is 20th century reanalysis, so it goes back to 1871, about 6-hour resolution. And then this is a paleo data set that takes us back to about 200,000 years. So Greenland, oxygen 18. And so there's one adjustable parameter here, which is the calibration of the paleo temperatures. So that's being moved up and down so that they match here. And you can see that roughly you've got power law, weather regime, I call it. You have some intermediate regime up to something like 100 years that I call macro weather. And then the lower frequencies, 100 years and longer, out to about 100,000 years, are climate. So I'm going to go into this part here in a lot of detail in about 2 weeks, but today I'll concentrate this part here. But just to give you an idea that these different scaling regimes, this is just an annual cycle, of course, the different scaling regimes correspond, of course, to radically different types of behavior. So, for example, if we're looking in the weather regime, we could look at, this is at 15 hertz, this is at 1 hour. You can see that the typical temperature fluctuations are a bit like a drunkard's walk, in the sense that the longer you wait, the larger the temperature difference is, the larger the fluctuation is. When you go, though, to 20-day averages, which is in this, so now we're taking data that's being averaged to about here, so we're looking at essentially this regime here, which is closer to white noise, still not white noise. You can see that you have a rather drastically different behavior. So you have a fluctuation that goes down, followed by something going up, followed by something going down. So you tend to have cancellation. So if you can imagine that if you average this more and more, that the values converge. Right? So this is the idea, when people say the weather is what the climate is what you expect, the weather is what you get, right? As a kind of a definition of the difference between weather and climate. That is, the more and more you average, the more and more you converge to something. So that's exactly what you see in this macro weather regime. So you would think that, okay, if I take data now at, say, 100-year resolution, I'm going to have to use paleo data, that, everything would be very nice and smooth, practically no variations. But, of course, it's not at all like that. Every point here is 100 years. And you can see, once again, it looks very much, in fact, one of the exponents, this H exponent here, that I'll mention in a moment, is almost exactly the same as in the weather regime. So again, the longer you wait, the more and more the fluctuations get bigger. Okay, so in fact, looking at this in the real space instead of in Fourier space, the previous thing, you see that, and this is the kind of this fluctuation type of turbulent law that I was discussing. So you have the average fluctuation. These brackets means averages, statistical average. Then you've got the average flux, which is just a constant, times the separation in time to some power h. So if h is positive, then you can see the fluctuations grow with time, and if h is negative, then they decrease. You have h actually is about 0.4, minus 0.4, and plus 0.4. So you can then look at this, actually work out, and I'll go into this. Actually, you need to use something a bit better than just a fluctuation difference to define fluctuations. These are actually using essentially Haar fluctuations, which are essentially Haar wavelets, but you can interpret them very simply so that the fluctuations grow out to about 10 days, and they decrease, and then they grow again out to about 100,000 years. Okay, so roughly, and you can interpret the fluctuations directly in terms of changes in temperature, and then this is the glacial interglacial temperature difference of about plus or minus 2 to plus or minus 3K at about 50 to 100,000 years. Okay, so anyway, so that's what I'll be discussing in 2 weeks. And you can see, right, of course, there are these power laws, essentially. This is just the global temperature isn't the same as a kind of a local temperature. All right. So, okay, so this is just the last kind of bit of this survey here. So you've got the weather, where the fluctuations are growing with scale. So the weather is what you get. You have macro weather, which is this intermediate regime where the fluctuations decrease with scale. It's actually called macro weather because essentially if you just extend weather models, either turbulent-based weather models or numerical weather models without any climate forcing, what they call control runs, then it reproduces these statistics and these statistics extremely well. Okay, so for the climate models to get the climate, of course, then they need something else. They need climate forcings, and the question then arises as to whether the climate forcings that they put in are adequate for getting the statistics. And this turns out to be a problem. Anyway, we could discuss that later. So, okay, so in that sense, the climate is not what you expect. Right? The climate is actually this other regime, which is just like the weather regime is. Yes?
Yeah, just a comment. So basically, going to some classic literature in climate, like Barry Saltzman. So basically, on one side, okay, the weather part is clear. What you're saying is that what becomes interesting dynamically is what we used to call the dynamical paleoclimatology. So the dynamics taking place on very long time scales. So that is again very interesting. What you have in between, it's somehow not as interesting. You see the macro weather. You get it's something that is constructed as an average somehow. So to me, I interpret this as that the interesting dynamics occurs small scales, and we have many instabilities going on, like baroclinic instability or convective instability. And the last one, on the longer scale, we have something like ice albedo feedback becoming involved. So in between, we have.
Well, yeah. In fact, if you're looking at what they call the millennium models, right, which go back 1,000 years, then the main forcings, aside from anthropogenic in the recent century, if you go, say, 19th century and earlier, then it's essentially volcanic and solar. The only things that are really important, or at least considered important. But actually, if you look at it, and they're not sufficient. In fact, they don't give you enough variability. But I wanted to, this is a very interesting discussion that I wanted to have later in 2 weeks. So I just wanted to give a kind of a quick overview. Yeah, oh, sorry, yes.
Yeah, you partially answered my question, I think. I was going to ask you what you meant by climate forcing. So this is, if I understand right, what physical processes you include and exclude to most efficiently get climate data in your model?
Well, the thing is, the GCMs, like these global climate models, if they don't put any changes in what they consider the boundary conditions, which could be solar changes or volcanic eruptions and stuff like that. If they don't put any fixed boundary conditions, then of course the model does indeed converge to its climate. And the way it converged, so it just gives you macro weather. You can go for tens of thousands of years of simulations, And you're constantly, whoops, I pushed the wrong button there.
Take care of the butterfly effect.
Whoa. Oh, this, what have I done now? This thing is not going back. Oh, that's cool. I did something stupid. Now it's not responding. Oh, heck. That, yeah, it's, the thing seems to be frozen here. Sorry? What do you think I should do? It's not going. Oh, that might work, yeah. No, it does not. Ah, okay, you got it out.
But this we are just discussing is with Paul. This would mean that, for example, the IPCC actually simulates macro weather because they simulate what you say 25, 50, 100 years. So in some sense, it's good news. I mean, you don't like it, but what the...
Okay, well, actually, no, I really would like to discuss this, but the thing that you find is if you look at the 20th century, where the anthropogenic forcings are important, then that really dominates everything else. So you can put in all the solar and all the volcanic you want in the 20th century, and it's small. It's a small forcing compared to the anthropogenic forcing.
Well, I mean, then you go into further detail. In the context of your classification, and the comment you made, is actually for the predictability, the macro weather regime, which the IPCC uses, in essence, they don't go much further. But that's actually good news, if you wish.
Well, except that what I'm saying is, though, that it's not macro weather as soon as you put forcing. So the variability goes way up because of the CO2 forcing. Okay, so anyway, but in fact, okay, the macro weather turns out to hold until about, well, here you can see this is globally averaged. So this is the macro weather, and it holds out to, here's 10 years, and then it starts to go up again. This is actually this is 1500 to now, this is paleo data, but it goes up, the transition, so this increase here is due to natural forcing. This increase here is actually due to CO2. So the transition point from macro weather to climate is closer to 10 to 20 years in the 20th century, and it's more closer to 100 years previous. Okay, so
one comment which makes sense in this sense. The standard, the WMO standard for defining climate is a 30 years average. And somehow it fits with the idea that this is the time scale over which, so 10 to 15, 20 years, you don't have that much going on.
it's the minimum fluctuations here, minimum RMS.
This is a normative. It's not something, it's more of a very empirical definition, but nicely enough it fits with the idea that is not like the most active region in spectrally speaking. So there is almost a gap somehow, not really, but...
Well, it's the minimum in the fluctuations.
Yes.
And the thing is, the actual definition is totally ad hoc, right? It actually goes back to the International Meteorological Organization, 1935. They decided that the climate normal was 1900 to 1930. And then after the war, when you had the WMO, they realized, okay, wait a minute, the climate is actually not quite the same as it was 1900 to 1930. You know, so we have to move to. They moved then to 1930 to 1960, and now it's 1960 to 1990. They kept the 30 years, but it's purely ad hoc.
Yeah, but the length.
But the length does, in fact, I mean, this is the first time it's clearly shown that, you know, the length actually does, in fact, turn out to be the minimum variability here. So you've averaged, so in a way, it's a logical thing. You estimate a climate state by averaging over all of the kind of the weather stuff, and then what's left over is stuff that really is change in that state due to longer term, lower frequencies.
So remind me, why is in the green curve, and why is there no anthropogenic effect?
This one is previous, this is 1500 to 1900. I didn't specify that. So it's not, so there's more, well, part of the thing is there's a calibration issue perhaps up and down, but the left to right is the most important thing, that the variability starts to increase more like 100 years previous to the 19th century, whereas in the 20th century it starts to increase at around 10 to 20 years. I mean, this goes back to 1871, this record here, so it's almost the longest that we have for global estimates of the temperature from instruments. This is based on paleo data.
And there's no anthropogenic effect in there.
Well, there's virtually none before 1900, okay. I mean, there was the CO2 in 1900 was very close to what it was in 1750, in fact. I've forgotten the numbers, but I mean, there's, in fact, a lot of people in climate don't claim there's not much anthropogenic effect before about 1950, but I mean, certainly before 1900. But no, I've got a lot of things to say about this, but I wanted to do it in about 2 weeks. Okay, so I'm just going to try and move on. So I want to first of all give you a kind of a simplistic, just to give you an idea about this H, because there's going to be two aspects to the models that we'll need for the weather regime scaling. You've got an additive aspect and you've got a multiplicative aspect. And the additive aspect is the easiest one, and that has to do with this H exponent. And you can very easily see how, what it means really by just this very, very simple fractal construction. So this is, say this is your generator of your, think of this as a fractal set, in fact, if you like, but thinking this is a function, this is the zero line, this is a plus and minus, so so it's the motif, right, that's the term. Okay, so you reduced all of this by a factor of 2 in the time domain, and you reduce it by 2 to an h power, well, 2 to the minus h power, actually, in the amplitude domain, and then you take a random sign. So, so one could be like that, one could be like that. And then you iterate this, and you can see that as you iterate more and more, to smaller and smaller scales, the fluctuations get smaller and smaller when h is positive, and when h is negative, on the contrary, the fluctuations get bigger and bigger. Then you add them all up, and then you get a function that has either fluctuations growing with scale if h is positive, or decreasing with scale if h is negative. And you can see what's going on here. The more you average this, you're simply, because these things have, every one of these sort of staircase things is got an average of 0. If you average over it, you can see that averaging is going to quickly get rid of all of this stuff here. Okay. So very simple way to get an understanding of that, but that's not going to be adequate for real data. So for example, this is temperature data every 280 meters for several thousand kilometers, so there's about 10,000 points here. This is the actual temperature. If you try and estimate the turbulent flux associated with the temperature fluctuations, you can do that by looking at the data at the smallest scale, say 1 pixel here, and dividing by the mean. And that gives you a kind of an estimate then of this prefactor here. So it does not have this H scaling in it. And what you get is the red thing down here. So this is just essentially the absolute first differences of the top curve. And you can see that it's incredibly variable and very far from being Gaussian. So this spike here is nearly 17 standard deviations. Okay, so quasi-Gaussian is completely ridiculous. So how can you try and understand that? So to understand that, what I did, this is just to give you the idea, right? You start with the data. This is exactly the same data I showed before, red. What you can do is, of course, you can degrade the resolution. This is by factors of 4, by factors of 4, by factors of 4. Notice the vertical scale, of course, decreases as I average, but you can see that there's still huge amounts of fluctuations, even lower resolutions, but eventually, of course, everything just has to become uniform. You've averaged everything out. And so the question that arises then is, well, if I want to make a model of this, can I do it by starting off with essentially a uniformity over the uniform function over the interval, and then going the other way by essentially breaking things up into bins and in fact multiplying them in this case. So this is the cascade idea. Right, so the original cascade idea, you have some essentially, it's supposed to be an eddy. Square obviously is the wrong shape, but isotropic, and then you divide up this just sort of schematic thing. You can divide it up, and of course, for some reasons, they're called daughter eddies. This would be homogeneous, so that all the energy flux, in fact, in this eddy that gets distributed uniformly, in this case, over the sub-eddies, and you keep going, and eventually you get down to dissipation scale. Okay, so that then is just has a dimensionality of 2. If you have an intermittent version of this where you kill off an eddy from time to time to imitate, the fact that the energy flux is not uniformly distributed, then so you can flip coins. Then, of course, you get a fractal set, and in this case, the fractal dimension reaches that. But more generally, what you can do is you can start with, let's say, the unit interval divided in half, so it's uniform to start with, and then flip a coin, and sometimes you decrease, sometimes you boost. Okay, so this is called the alpha model. And what you get, well, this is in 2D, so the vertical thing now is your energy flux, the intensity of the turbulence, if you like, and these are the two spatial coordinates, so you break up by a factor of 2 in each direction, flip coins, and you keep going and going and going, and you can see that when you get down, this is a factor of 128, that you get these spikes, and so actually this is a multifractal. The fractal dimension, if you just take a cut at some level, and you looked at all of the regions that exceeded some level of intensity, you'd have a fractal set, and then if you raise the level to a higher level, you'd have another fractal set, which would have a lower fractal dimension. Okay, so in that sense, it's a multifractal. It's actually a field, but mathematically, it's actually a singular measure that it actually doesn't convert. This is one of the interesting things. It doesn't actually converge at the smaller scales, which leads to so it only converges if you average, if you have to integrate it, in fact, over some finite set in order to get small-scale convergence. And when you do that, you get rather different properties for the extremes. And I'll discuss that conference next week on extremes. But you get what's called Dresde behavior, and you can see here I've gone back, I've taken this cascade to here, and I started going up this way to lower and lower resolution by just averaging. And you can see that if you compare, so this level here, for instance, I just have variability due to the larger scales, and then I stop at some point here. This one, I've put in variability at smaller and smaller scales, and then I've tried to average the variability out, and you can see that most of the time it works pretty well. These spikes are basically the same, but sometimes you get bigger spikes. And the thing is, here you actually get power law tails. So you have very interesting behavior associated with what's called divergence of moments or multifractal butterfly effect. But okay, so that interesting extremes that I won't have time to discuss today. Okay, so the basic statistics of cascades and well, this is just a toy model, of course. I'll show in a few minutes how you can generalize this. You don't have to divide up by factors of 2 and get all these ugly construction lines. You can make some quite nice simulations. But the basic idea is that, if you look at the field after developing the cascade for a range of scales lambda. So right here I have 128, so lambda would be 128 down here. If I want to get the statistics of the qth order moment, so these things are just statistical averages, then it goes as the scale ratio to some function. This is just a convex function here. And this k of q it's actually the second Laplacian characteristic function of the log of the process, in fact, the generator of the process. So, but it has all the statistics of the process in there. And also, of course, this is connected with the probability distributions and some kind of beautiful mathematics to connect the exponent of the probabilities to the exponent of the moments via Legendre transformation. But okay. So back 25 years ago, actually 26 years ago now, this was the best we could do to try and check out some of this cascade stuff. So this is our McGill radar here. So we were just able, we looked at some of the statistical moments, but you were only able to get really precipitation from, in fact, it's radar reflectivity. It's the Z, it's not even precipitation. In fact, it's the reflectivity due to precipitation, but we had resolutions going from about 1 to 128 kilometers, and then the curvature of the Earth means you can't really go further. You're starting to look over the top of the storms. So this was the best we could do, and we could only speculate whether these lines would continue. Maybe I should just mention, see, the cascade idea says that the qth order moment normalized by the mean to the qth power, that when, this is supposed to go as lambda to some power here, so lambda is the ratio of scales. So if lambda is 1, then 120 power, of course, is 1, and so there's no more variability. When you've gone to lambda, so lambda is the effective outer scale of the cascade to the resolution, and so what you'd expect on a log-log plot is you'd expect straight lines, but they would all converge at whatever the outer scale was. And all we could do that, 25 years ago was to speculate that they might more or less converge, right? And it doesn't, like here it would be 32,000 kilometers. It doesn't have to be exactly 20,000, which is the largest great circle distance, because this is an effective outer scale of the cascade. It would be the scale at which, if all the variability was due to a cascade, the scale at which the cascade would start. Whereas in actual fact, 20,000 kilometers, there's already variability because there are many different interacting fields. So in any case, thanks to this TRIM orbiting satellite, we could actually fill in the gap with real data, and in fact, it works very well. And yeah, there's a little bit of residual variability at 20,000 kilometers, essentially. So the outer scale is a bit larger, something like 30,000. And so here's the second order moment, these different moments. You can notice that the 0th order moment, which corresponds to rain or no rain, right, is dominated by, you use the convention that any number to the 0th power is 1, except 0 to the 0th power is 0. So in fact, the scaling here is not so good, but the reason is that the minimum detectable signal of the radar was very poor. In fact, you couldn't see anything that was weaker than about 3 times the average. So, and you can make models that reproduce this curvature quite well, but in any case, the higher moments scale very nicely. You can do this. Oh, this is reanalyses, north-south wind, east-west wind, temperature, humidity, and you can see that the scaling is really rather good, and the outer scales are a little larger than the size of the Earth. You could do that. Whoops, this is. Oh, I have to use this. That's not true. Okay, right. This is a Canadian weather forecasting model. Actually, this is just this is the forecast. Oh, all right. The forecasts have almost the same statistics, in fact. So I didn't show them, but anyway, you can look at the forecast, you can look at the analyses. You had very nice scaling again. You can look at the energy, essentially the shortwave energy and the thermal IR. So this is from satellite data. Nice scaling again, that's from the same satellite as previous. You could look at, actually this is from aircraft, only up to about 1,000 kilometers. Again, you can see quite nice scaling. Okay. Just now, come back, because what I did is I first showed you, I said let's look at the fluctuations with respect taking an average of the turbulence. So you just have a delta t to the h or delta x to the h. It's this h exponent that I modeled with this kind of step function toy model. Then I showed you a multiplicative model for the turbulent flux corresponding to a multifractal cascade. And now we can combine both to get a model of the whole process. So this is just, still at the level of a toy model, but you can combine the H model, which would give you, for temperature fluctuations, which would give you a linear exponent, QV, capital H there. Here is the alpha model, which gives you delta t to the minus a k of q there. So this is now a convex function. And so the variability goes up like that. If I multiply these together, I get the thing on the right. And then I have to add all these things up, and I get the simulation down here, which has both exponents. So it has a linear part and then a nonlinear part. So I need to get a process which corresponds to that, but without this rather artificial construction method. So how do you do that? First, you could do the multiplicative part. So you say this is the multifractal cascade you want. It's multiplicative. How do you get a multiplicative process? Well, you can exponentiate an additive process. So the additive process gamma is the generator. The generator could be proportional to, there's an amplitude factor, so that tells you in fact the codimension of the mean. And okay, so that's actually quite important, but just a number. You've got an IID, we use Levy noise, index alpha, and you can convolve that with a singularity over a certain range here. And so in Fourier space, this convolution with a power law is in fact a fractional integration, and it corresponds to a power law filter in Fourier space. So in Fourier space, it's quite simple. The statistics of the epsilon that you get then are indeed like that, but with k of q defined by these two things, the C1, which is the amplitude here, and then the alpha, which is the Levy index alpha. So you get a two-parameter thing here. And in fact, the reason of course, for looking at these Levy processes is that there's a kind of a central limit theorem for multiplicative processes, right? Just as for additive processes, the central limit theorem that gives you Levy distributions. If you have a multiplicative process, then it's essentially log Levy distributions, but the problem being the small scale limit I alluded to. So it turns out that this behavior is indeed universal in the sense that it's not sensitive to a lot of the details of the process, but the tail is going to be different. It's going to have this power law, and the exponent here will depend on the process, but also it will depend on the dimension of the space over which you integrate the process. Because a completed cascade, as I mentioned, in order to converge, it has to be kind of like a generalized function, basically. You have to integrate it over some space, and the statistical properties depend then on the dimension of that space. Okay, so that's to get the multiplicative part, cascade part, the nonlinear part in the exponent. The actual process, say the temperature or wind or whatever, is going to be given by the turbulent flux convolved, another fractional integration. And so in Fourier space, again, it's just a power law, so it's just the last power law filter, so that's a linear operation, of course, and that just gives you an extra linear term in the exponent. And so when you look at, say, the qth order structure function, which is just the average of the qth power of the fluctuations, then you find that it has this exponent with, so you have the linear part, and then you have the nonlinear part here. Okay, so, all right, so that's the kind of recipe. And when you do that, you can make some nice simulations. You don't have these straight line structures anymore. So here you've got, this is actually part of a 3D cloud simulation, and I've actually made it anisotropic with stratification and stuff. So this is a side view, and this is a top view. But then you can do radiative transfer calculations, say what would infrared signature look like. You can look at what it would look like on the top if it was lit from the side, or what would it look like at the bottom. And okay, so anyway, it's very easy to make all these things, but that's all very well if you have isotropy, right? So all the time I've used up till now, the notion of size was simply the usual Euclidean notion of distance. The modulus, say, of a vector is the size of the vector. But that's not adequate to deal with things in the vertical, and in fact, but it turns out it's actually quite straightforward to handle stratification. So, for example, what I've talked about up to now is this is my usual notion. This is just the vector norm. I've got to replace it by a thing called a scale function. So I put 2 bars, and the scale function basically satisfies this scale equation here. And so this says that if you want to blow down, this represents a blowing down of your vector, reduction of your vector in an anisotropic way, in fact, by some generator G, which in the simplest case is just, say, a matrix. It'll be linear, generalized scale invariance. Then that reduces the scale by a factor lambda. Okay? So very simple case that we need for stratification would be that the scale function might look like this for, say, Z would be a vertical coordinate, X horizontal. LS is called a spheroscale. It's the scale at which things are roughly roundish. And you can see that if this thing hz is 1, then this, of course, just reduces to the usual Euclidean distance. So any vector on a circle here has the same, it has the same length, right? You start the vector in the center out to the edge, it's got the same length. In this case, though, if hz is not 1, then you get, these are the contours of isoscale. And what you can see is that at small enough scales, the structures are kind of vertically oriented. At large scale, they go the other way. So this would be the simplest model that would handle vertical stratification. You just have a simple matrix like that. And actually, it turns out that hz is about 5/9. You can check this. There's all kinds of ways of checking this, but I could go on and on about the problem of aircraft data. Turns out that people were trying to measure the spectrum of the horizontal wind using aircraft, and the problem is that the aircraft don't stay on ISO heights, that they, well, often people try and put them on an ISO bar, and the ISO bars, though, are not flat, and at some point, the spectra ends up being dominated by the statistics due to the vertical change in position of the aircraft rather than the horizontal. And so what people get is a transition from about k to the minus 5/3, in fact, to about k to the minus 2.4, which is the vertical exponent. And that has been systematically misinterpreted as k to the minus 3 by people who try to support two-dimensional isotropic turbulence or geostrophic turbulence at large scales. But to try and settle this, we decided to look at the delta x delta z structure function. So look at the fluctuations in this is then in the vertical in a vertical section. So using a huge number of aircraft flights in the U.S. Anyway, you get extremely good fits, and this thing hz is indeed close to this I call theory value 5/9. The 5/9 actually, all right, I don't have time to discuss where that comes from, but basically it comes from, well, here I guess is enough information. You've got Kolmogorov law in the horizontal, so you say energy flux dominates in the horizontal. In the vertical, you have a buoyancy buoyancy variance flux dominated statistics, essentially Bolgiano-Obukhov. So you have dimensional arguments that say you get delta x to 1/3 in the horizontal, delta z to 3/5 in the vertical, and you put those together. It turns out hz has to be the ratio, 5/9. And so structures change volume then by 2 plus hz, because you have a structure size L in one of the horizontal directions, L in the other direction. The vertical is going as L to the hz. And so this tells you how essentially the volume of, in fact, non-intermittent structures changes the scale. So if you have a two-dimensional atmosphere, then the thickness of a structure is essentially independent of scale, right? So this would be the way larger and larger structures would look. If you had a three-dimensional atmosphere, then structures are just say roughly spherical at larger and larger scales on average. And of course, then you have the problem that the finite thickness of the atmosphere would have to cut that off. And then you have these intermediate models. And this one actually seems to be closest to the data, and you can see the structures get flatter and flatter at larger scales. So okay, right. Actually, why don't I come back to that one in a moment, just to give you more the idea. So what it means is this is your multifractal simulations of a vertical section. So I zoom in to such an atmosphere, and I zoom and I zoom and I zoom, and you can see things are slowly changing because the aspect ratio of structures is changing systematically. So it's small. So I start at large scales, I get lots of stratification. Small scales, then I get things that are more round. In fact, the spheroscale is about right here. You can see structures are roughly roundish. This scale here. All right. Just to give you an idea that numerical models of the atmosphere actually unwittingly acknowledge the 23/9 dimension of the atmosphere by the way they've developed the vertical extent of the models compared to the horizontal, right? Because nobody in their right mind, if they wanted to do certainly a global model, would have the same number of same resolution, say in the vertical as in the horizontal, for obvious reasons. And so all kinds of choices have been made to sort of, in a maybe somewhat ad hoc way, to how many vertical levels you put in the model, given that you have a certain computer constraint and you have a certain horizontal size. And so if you actually put the historical development of models here, you can see that actually it fits quite well, that people have been respecting this stratification even without knowing it. One can look at, this is actually aircraft data, the aircraft flying along here with a LiDAR. You can just see visually the data is 3-meter resolution in the vertical and about 100 meters in the horizontal. This is actually Rocky Mountains, the black, this is near Vancouver. But you can see that globally, and this is backscatter from aerosols, essentially pollution. You can see that at large scales, everything is pretty stratified. And you can then use the data to zoom into this box and look at the thing at the full resolution. And now you can start to see that structures are starting to go the other way at smaller scales. Also see some hints of wave-like stuff. But when you analyze this data, so you can look at what is the relationship between the vertical extent and horizontal extents of structures. These are for 9 different aircraft runs. You can see that the relationship is pretty close to the 23/9. The statistics get bad at the larger scales. And that, interestingly, the scale at which structures are roughly isotropic can be determined by just extending this thing back to see where it intersects the bisectrix. And so you get essentially between, I know this would correspond to say 2 meters, and this is about 20 centimeters. So depending on the situation, the scale at which things are roughly roundish varies from, say, 20 centimeters to 2 meters here. And on the other hand, if you extrapolate the other way, you see structures that are essentially the thickness of the troposphere would be about 10,000, 20,000 kilometers in size. Okay, so then you can make more simulations with have the stratification, and you can put some radiative transfer in there to make it a bit more realistic looking. Anyway, so you can play around with that quite a bit. Okay, so what does that mean? It means that the cascades then are going to be anisotropic now. So in this case, you have a vertical structure. This would be a vertical section. You break it up into smaller structures. Homogeneous cascade would be like that. Let's say you break it up by a factor of 4 in the horizontal and 2 in the vertical to get the vertical horizontal anisotropy. And then you can also have the intermittent version where some of the eddies are dead, alive, and you can check that indeed this is the same data. You can analyze the data in the vertical and the horizontal. You see the outer scale in the horizontal is indeed about the size of the planet, whereas in the vertical it's a little bit greater than, say, 10 kilometers. You could look at dropsons. These have about typically 5-meter resolution. This data this is based on 238 or something, and you get wind, horizontal wind pressure, density. This is the vertical wind of the velocity of the sonde, in fact. But again, you get quite nice scaling with outer scales between about 1 and 10 kilometers. Oh, and these are the thermodynamic variables again, quite nice. So it's totally different. Still a cascade structure, of course, but not the same as in the horizontal. Okay, so the last part of my talk, I guess I'm going to have to stop in a minute, but the last bit was on, so what you do then about going to space-time. So I've said, okay, fine, we've got evidence for horizontal scaling pretty much up to the size of the planet. You've got vertical scaling through the troposphere, but it's not the same. But if the wind field has this scaling in space, then the wind connects space and time, and you'd expect to get scaling in the horizontal. In time. You'd expect to get it in time. And so let's see how we can try and take that into account. And of course, classically, you don't have scaling. There's all kinds of diagrams like this. People have classified things. So this is called a Stommel diagram. This is the type of thing you see in all kinds of meteorological textbooks. Actually, this one was stolen from a guy called Steele. Forgot to mention that. Sorry, that's a bit of a pun, I guess. But yeah, it's Steal. Right, Steele, as in. Anyway, but okay. So you say, I'll find at a certain different structures of different sizes live a different length of time, and then the interpretation is that you need a different theory for each of these different structures. But actually, it turns out these structures are all pretty much on a straight line on a log-log plot. And not only that, but the central line here actually corresponds to theory. If you had the essentially Kolmogorov scaling in the horizontal, energy flux domination in the horizontal, and with, in fact, the observed energy flux. And these lines here then take into account the intermittency, say 1 standard deviation in the relationship between the lifetime and size. And so actually, you could kind of predict this diagram based on the fact that you don't have different, you just have a single underlying dynamic. Okay, then you could check, say this is just, okay, precip data. And what you see is, right, you get nice scale. This is at hour data. It looks like the cascade starting at something like 40 days. The statistics are pretty good up to about a week. And then you get this macro weather. Okay, I call climate, but it's, in fact, over here it's mostly macro weather out to about 30 years. But, okay, so just maybe, I know you're mathematicians mostly, so I haven't given you any serious equations, or practically none. Let me see if we can try and understand that a bit better. Just to sort of fix ideas, we could start with a very simple example, which would be a classical wave equation. So I is your wave amplitude, or your field, which is studied, and this is the forcing F. So the usual way of solving this could be, say, by Fourier transforms, and G then is the propagator, and so it just is dependent on the frequency and the speed here and the wave vector size. Okay, so classical wave equation then, the propagator satisfies this symmetry. So you blow down, this is a horizontal, this would be for a horizontal vector, say, wave vector and frequency. It would satisfy this with h equals 2. So now what we can do is say, okay, well, we would expect here that we're going to have some anomalous exponent. Instead of 2, that's, we're not expecting something like a classical wave equation, but we might end up with, say, a fractional wave equation. And we'll come back to that. But of course, the fractional wave equation has the same dispersion relation. The dispersion relation doesn't depend on h. So, okay, so just bear that in mind, that we might not be able to really distinguish. If we're just looking at dispersion relations, we couldn't tell the difference. But okay, so what would be a kind of a turbulent propagator? That's okay for a wave propagator, and in an implausibly classical case, just as an example. But what would we expect for the propagator, space-time propagator in turbulence? Well, this what I call fractionally integrated flux model that I just described a little earlier, this multiplicative and additive process where you fractionally integrate this turbulent flux, you could write this as essentially your field, then in Fourier space is just the product of your turbulent propagator times the forcing, essentially the energy flux. And say, so Kolmogorov, you'd have these values, and this is just purely in space. So this is, maybe you'd call this more like a Green's function, but instead of a propagator, because it's just in space. So this would then be isotropic space and to some power. Okay. You can do an anisotropic extension. You just have to replace the vector norms by a scale function, which satisfies this type of equation, and you have linear generalized scale invariance, and that could be some matrix. And you might get some scale function like that, if you have a very simple case. Okay, so now it turns out, all right, so you could say, what happened, you could say, okay, fine, we're expecting the system to have Galilean invariance, but the velocity that's transporting the eddies is essentially a turbulent velocity, large-scale turbulent velocity, and so you've got to take into account that it has statistical variability. And all right, you can do some not totally rigorous math, I must admit, but you can make a fairly good argument that the propagator should look something like that at the end of the day. So you have to, the frequency is a bit modified. It's modified to take into account a mean advection mu, and then the variability of that mean sigma. And then the scale function here can take into account, in this case, it only takes into account the trivial anisotropy north, south, east, west. So it could be much more complex, but this is a simple model here. And so, okay, so that's how you could take into account a turbulence. But actually, you also have waves, right? So I just used this idea of Wheeler-Collattis that well, they didn't express it quite like this, of course, but essentially that you have a multiplicative relationship in Fourier space between a wave part and a turbulent part. So what are the constraints? I mean, the idea is that if the statistics in space are constrained, so we're talking about High-Reynolds number statistics in space, if they're constrained by symmetries, essentially scaling symmetries, and you go to space-time, and you still have space-time symmetries, and I'll actually show you some more data on that in a minute, then what kind of a constraint does that give to, say, wave propagation? So there's a couple of constraints on the propagator that you have say it's a propagator corresponding to a real function. It has a scale symmetry in space and time, and also you need to respect causality. You can work out a general form for what that could be. Okay, so putting all of this together, one simple thing would be just this fractional extension of the wave equation, except with a different exponent there. And okay, so you could get then a overall propagator squared, which would be, you could try and measure from the spectral density in k omega space, could look something like this. So you'd have some singular part here, which would give you a dispersion relation, and then you'd have a turbulent part, which would in actual fact be quite dominant, except near the singularity. And so anyway, if you look at data on this, you can look at, this is from IR data hourly for about 2 months. You can see that, this, so okay, so if you have this symmetry for the propagator, so that this would be horizontal wave number space and frequency space, a 3D space, that the thing has this, if you just blow down the vectors, you get the same form, but with a factor here. Then you'd expect that the 1D spectra for just, say, east-west, north-south, and frequency would all be power laws with the same exponent. And so this is what this is testing. So we've actually worked out, of course, the whole spectrum, but then this is just 1D sections, and you can see that it's extremely accurately. The only thing, the main deviation is the diurnal peak, which is, of course, not seen in space. This is a harmonic here. And actually, even the deviations, this thing is slowly curving, but that's just, a lot of that is just an artifact of the fact that we have a finite size domain, and so actually the main deviations start to appear at around 5 or 10 days over here. Okay, so the symmetry is well respected. You could look at subspaces. Okay, I'm just about done. I'm sorry this is maybe overly complicated, but you could just, you could do a fit to this sort of overall form, which is in fact really just a kind of a crude guess when it comes to the wave part. The turbulent part has a reasonable basis, but did you find that even with no waves, because the wave part is actually very small. You have the turbulent part gives you a variation of something like 10 to the 5 in your spectral density over this range here, and the residual, what's left over, turns out to be only a factor of 2 to 4 variation. So the wave part is actually quite small. So you put no waves, you actually get pretty good fits to these different subspaces. If you put in a bit of waves, but just a classical wave equation, you do a bit better with some fractional exponent here. But you do even better if you take into account that it's not a classical wave equation, but you have some other thing that looks like more like Kelvin waves, and you can do even better, but these exponents are pretty small. If you just isolate the wave part, I don't know if people know Wheeler and Collattis work, but they did the same type of thing, but at actually about 10 times larger time scales. But what you get here is, though, you have east-west wave numbers, and you've got frequency. So this this red line is actually the theoretical prediction for Kelvin waves. The green line is the maximum of this thing here, and the blue is the contours from this theoretical thing here. So I think we get, we can reproduce the Kelvin. I mean, this is, in fact, pretty ad hoc, actually. So there's a huge amount of possibilities. But anyway, we think we can do reasonably well. So we don't need to linearize the equations and pretend that Reynolds number is near 1 when it's actually more like 10 to the 12. And then you can make simulations which have different degrees of waves and change the exponents and stuff. Oh, last little thing, I forgot about this. I don't know, maybe I should just stop now. But okay, well, you can do prediction, you can stochastic forecasting, and okay. So, all right, so I'll stop there. Yeah, so I'm sorry to, have gone over.
Okay, so we have some comments or questions or requests for clarifications.
Yes, Nathan.
I didn't mind. You, at some point towards the middle of your lecture, kept using the word dimension. So there's the 3 dimensions, and then there's 2 dimensions, and there's 2.5, and now there's 2. Can you, you may well have explained that well, but I sort of missed. What
Okay, no, I didn't have time to. Well, I mean, there's this thing called the elliptical dimension, which is just essentially how does the volume of non-intermittent structures change with scale. So, in 3D that would be just 3, because if you increase the scale of something, you just blow it up by a factor of lambda, then the volume increases by lambda cubed. So D is 3, and 2D would be lambda squared. So say the thickness is fixed, and you just increase the scale then of a 2D structure, would be lambda squared. So the 2.55 is just saying that the vertical extent goes as the horizontal extent to the 0.55 power, the 5/9 power. So if you blow up a structure by a factor of lambda, the volume increases by lambda to the 5/9 plus 2. That's 23/9. So that though doesn't take into account intermittency. That would be, for non-intermittent structures. So if some of those structures at a different scale that might be killed by, or more or less killed off by this intermittency, the cascade process, so they would have dimensions that are less than that. So this elliptical dimension is like an upper bound on the fractal dimension of sets that you could have. Okay, so I don't know if that's a better explanation. But that's why it's pertinent that, the numerical models, basically it's like, they are defining the largest space that any structure can have. And so that's why it is pertinent to look at the number of vertical pixels as a function of horizontal pixels, and the fact that they've made this choice corresponding to 23/9 is probably significant, but anyway. But the actual active structures at any scale then depend on this, actually it's a codimension function related to this K function I talked about. So you've got and then a whole hierarchy of structures that are more and more intermittent.
Okay, so
as you go to
this could be a function both intermittency and the anisotropic structure of the.
Well, the thing is, it turns out the key is the exponent on the probability distribution, then, which is a codimension. So it's actually not a dimension. It turns out if you're looking at statistics, it's not the dimension that's important, but the codimension, which is the difference between the dimension of the space and the dimension of the set of points you're interested in. That's the codimension. And so the codimensions actually, if you go to an anisotropic space, the dimension would be changing because of the anisotropy, but the codimensions can be the same. It can be unaffected, in fact, because it's the fraction of the available space which is occupied by a structure at a certain scale. Right? And the way that changes with scale tells you the codimension. So it's essentially a probability or a fraction of the space.
The whole of the wave propagator that you use, is that sort of unique, or are there several choices, let's say, because you don't have this equivalence that is usually given by a spatial Fourier transform also, if you go to these more complicated scaling wave propagators. How much is there input in a sense that you choose this ansatz, or how much is there other choices possible?
Okay, well, okay. I mean, the fact is it's pretty vast because the only constraints I'm using on the propagator are the fact that, okay, reality, so that you're saying the wave is in real space. You have causality, you want it to be causal in space-time, and then you use this essentially it's isotropy in the horizontal and in time, which I justify from the data, but there are some theoretical arguments about eddies being swept around. I'll go back to Tenikes and whatnot, but that would support that. So if you just say what propagators satisfy these constraints, then you get a rather general answer here. You have three essentially arbitrary functions, and these are angles. You have to look at spherical coordinates in kx, ky, omega space. And so it's actually incredibly general. And so we couldn't get anywhere with the data without kind of guessing something. And that's why we went to first essentially this classical, this is just a fractional extension of the classical wave equation, but that's east-west symmetric, in fact. Well, okay, there's a slight generalization because I took into account north, south, east, west, and isotropy. This scale function isn't quite, if A was 1, A turns out to be 1.2. So, okay, but essentially this is a straightforward extension of the classical wave equation. But it turns out that this is a much better approximation because it gives you east-west asymmetry, which is what is observed and what you need for Kelvin waves. So with that you get the maximum is this nice green line, and this would be your Kelvin waves. That this actually comes from Wheeler-Coladas work. So, okay, but I mean, there's a huge amount of. That's why we really think that, I mean, I didn't mean this talk to be about waves in particular, but there's a contradiction that our understanding of turbulence is that high Reynolds number phenomenon, but within any region there'll be regions of calm, and there will be regions of extremely violent events, and if you look inside the region of violent events, comparatively speaking, there will be calm. So it's a hierarchical structure, and so the usual argument for using, say, linear wave theory in the atmosphere is, but there could be large regions of laminar flow in low Reynolds number. The only problem is nobody's actually observed such a region. Whenever anybody looks at the spectrum of any region, they're always getting, k to the minus 5/3. They're getting, so I mean, the Reynolds number is simply enormous, but but you have regions which are just much calmer than others, and that's just the nature of high Reynolds number turbulence. So how can you justify linearizing the equations? So I'm saying you can't. What you have to do is you have to say the scale symmetries, though, can still constrain the propagators. And I think, I haven't, of course, proved it in the general case. This is just the single we looked at here. But you can get, you can make propagators which satisfy the scaling symmetries that can fit all kinds of, dispersion relations. And people never look at the exponent of the propagator. They look at the dispersion relation, and they don't, they test the dispersion relation, in fact, only in limited ways. But nobody actually checks the exponent to see if it's really an integer, which is what linear theories would predict. Right? So my answer is that probably, they're getting more or less the right dispersion relationship, but the wrong exponent, and the reason for getting it is not really a good reason. But anyway.
Just a comment on the problem of the horizontal versus vertical properties. I mean, usually assumption on quasi-geostrophic turbulence, on, I'd say, geophysical turbulence, assume, say, the atmosphere is almost 2D, so things should be more or less 2D. But in fact, the temperature difference between equator to pole is about the same as the temperature difference between the surface and the troposphere. In the top of the troposphere, not by chance again. So there is a problem that the thermodynamics instead is very square, as opposed to the aspect ratio. And the other problem of quasi-geostrophic turbulence is that it is a quasi-2D theory, but it assumes constant stratification. So you are basically taking out of the system some properties that depend on the small scales. So that is, I think, an aspect that one is to be considered, that if we impose some rigidity in the system, of course we get some properties out which can be spurious just because we made an answer which is good at a large scale, not necessarily at all scales. So that's an aspect, I think, just to general problem of why it's so difficult to construct a theory of atmospheric turbulence. And so there are various approaches. But
yeah, I mean, essentially what's happened historically is you had a choice between isotropy symmetry and scaling symmetry. But what happened was people said, let's assume isotropy, 3D isotropic turbulence, 2D isotropic turbulence. Geostrophic turbulence is like slightly more flexible variant than, say, Kraken 2D turbulence, but it's still 2D. So so then you're forced to hypothesize a mesoscale, a break in the scaling.
yes,
And that's why there was so much interest in trying to find a break in aircraft data. And that's why we've been fighting for so many years to convince the community that the breaks that people see in the aircraft data were spurious. Why spurious? Simply because the aircraft did not fly on a flat trajectory. They were, well, I could go on and on about this. There was a whole debate with Eric Lindborg and Freydick and Sharman and a few other people in the last couple of years. But I think that this paper came out about a year ago in GRL, my student Pinel, where we looked for the first time with very high accuracy, because you need high accuracy measurements to test this, right? Because you're trying to distinguish the difference between aircraft going on essentially an ISO height and an ISO bar. So you need GPS altitudes, and it's only recently that we've got enough data with high enough accuracy to do it. But you could then get the 2D structure function, delta Z and delta X and delta Z, and it works out very nicely.
okay. Other comments or questions? No, I guess we.